Hi guys, welcome back to the Astro Imaging channel. Tonight's session is on Astronomical Seeing by Gaston and Baudat. We don't have an image of the week this week. We're going to launch one tomorrow, so you'll see that pop up, and we'll give the person an opportunity to get on over the course of the week. Remember, you can submit for the image of the week on Google+, and we'll try and reshare that so you can see where it is. And also remember, we've got a new website, so you can check us out there and see all of our past sessions. And if you need to contact us for any reason, that's the best place to find us, theastroimagingchannel.com. And if you wanted a T-shirt, that's also the way to get us. But as I see the room filling up, I'm gonna actually hand it right over to Gaston. Gaston's right here, and there you are, Gaston. You're live.
Thank you, Adam. Let me share my screen. Full screen, right?
Full screen, yes. There we go. Perfect.
Now it's okay?
Yes.
Okay. So I put together some slides. So the first things I want to say is a bit the scope of the presentation. And, I'm going to focus on astronomical seeing because it's what is our main concern. And it's about the effect of the atmosphere on astronomical objects. And the atmosphere, the turbulence of the atmosphere creates some problem, as you know. And in this presentation, I'm looking at essentially the impact of the distortion of the wavefront from the atmosphere. Typically, the atmosphere creates two issues. One is scintillation, variation of intensity of the wavefront, and that's usually not the dominant problem for us. The more important one is phase effect, the change of the shape of the wavefront. So the presentation will just ignore the scintillation effect. And as you can see here, when the wavefront comes from the space, then something happens in the Earth atmosphere. So the wavefront distortion of an incoming wave, let's say a plane wave, from the Earth atmosphere leads to some phase error. And if you think about a plane wave, the result basically is something like that. The plane wave gets some level of oscillation and distortion. And typically what we do, we look at the variation, the delay, if you wish, between 2 points of the wavefront, the error, which is a phase error. And in this example, the phase error for a given distance between 2 points of the wavefront, usually we use r for the distance, is a function of the distance. And this delta phi r is either in wavelengths or is given in angle, like radian, and 2 pi radian is just one wave. Now, in terms of nature of the phase error, what typically you see is on a long range, on a long scale, you see a tilt tip of the wavefront. And that's a dominant effect, and specifically for us with the size of the scope we may have. There is also higher type of order effects coming from the atmosphere, which is the roughness of the wavefront, so higher order, higher spatial frequencies. Now, if you have a small scope, and most of us do, the main effect you may see is a tilt tip, which is the image of the star, for instance, gets some level of wonder. With a larger scope, you will start to see some level of speckle. And I come back to that a bit later. So the source of the optical distortion is coming from the energy which is transferred from the atmosphere. When the atmosphere is moving, you have winds, there is some energy which is transferred in form of turbulence, and it's basically a cascade. And the two fundamental points here is there is an outer scale, which is the large L0, and an inner scale, which is a small L0. And if you look at the drawing over here, and it's a sketch of the problem, when the air flow that way, it will create turbulence. And you have first large eddy, and those eddy will eventually become smaller and smaller through this cascade to a level where they may be a few millimeters. And then they will disappear because friction. Basically, they are transformed in heat. So from an energy standpoint, there is what is known as the injection range. And this is where the energy of the atmosphere coming from the motion of the atmosphere inject energy at the highest, outer scale level, where the size of turbulence is typically between 10 meters to a kilometer. And those turbulence will go from those large scale down to the inner scale, to the millimeter. And eventually the heat will take over. What's important to remember is the energy involved in the process is a function of the size of the eddy. The bigger, the more energy is involved. And of course, because the eddy are made of different air density, there is different index of refraction, and this is why we see some problems when we image through the atmosphere. There is a model which is very often used since a while from Kolmogorov, and that's a model of turbulence. The guy is, I think he published his first paper on that topic in 1941. And the model assumes some things like the outer scale turbulence, the bigger eddy, are infinite, which is of course not the case in reality, and we should come back to that later. But the model gives you pretty good idea of what's going on in reality. And if you look at the model, basically what it does, it gives you an idea, a description of the variation of the phase across the field. And if you look at this equation here, this is the variation of the phase. And as I said before, the phase can be in a radian, an angle, or in a wavelength. And the variation of the phase is a function of this ratio r, the distance between 2 points of the wavefront, over some r0. And this r0 is known as a Fried parameter. It's a coherence length, and for most of gases is few centimeters across. What you can see here is an example in gray level of the wavefront error, the phase one. So you can imagine the wavefront is coming toward you through the screen, and in gray level from dark to light, you have the phase error, and in this example is for -15 to +25 wave. And here that will be the R0. R0 is when the phase error is roughly 1 radian, which is lambda over 6. And for any distance between 2 points R, this equation tells you how much phase error you may see. Now the Fried parameter is very important. In fact, if it's known to be R0, it's a diameter. And that is a diameter for which the RMS phase front error is about 1 radian. Again, it is 6 of the wavelengths. This is, if you wish, the average size of the turbulence cells, basically, across the whole atmosphere, of course. So if you look at the equation to compute R0, it's a function of few things: the wavelengths, the zenith, and an equation here, which is an integral, which has to do with the profile of the turbulence across the atmosphere. And most of the time, in a given scope of some diameter d, you have more than one of these R0, because R0 is more like 5 to maybe 10 centimeters across. And the result of that is this average cell size is going to create some distortion and some speckle. And by the way, R0 scale as 6/5 power of the wavelengths. So it goes up when the wavelength goes up, so which means the thing is better with longer wavelengths. So this atmospheric turbulence strength, the function I was talking about before, is a profile of the turbulence across the atmosphere. And if you look at it, in average, is what you see. There is a lot of turbulence near the ground, the boundary layer. And that's pretty much 1 kilometer above the head. of of the observer. Above that, you have a drop of the turbulence to roughly 5 kilometers. And then you see an increase of it to the boundary between the stratosphere and the troposphere at 10 kilometers above, roughly. But what's important to remember is most of the turbulence are coming from the boundary layer close to the ground. And this is an example of what's going on over time. Turbulence is not something which is always the same. It's evolving all the time. So seeing is evolving, And this plot is from the La Palma Canary Islands. And you see they have a way to probe the atmosphere. And this is the actual atmospheric trans function in red color from blue to red. You see the amplitude of this CN square function. It's a log, but whatever. So you can see there is still most of the time quite some turbulence near the ground, and depending on the time of the day, more or less turbulent atmosphere at the interface of the tropopause, and sometimes even in between. Now, what does it mean in terms of the quality of the image? R0 is pretty much like the diameter of a scope, which would be seeing limited. Think about a very large scope with a very large diameter. Well, if you have a large diameter, you are not going to be able to truly get access to the diffraction limit of your scope. You're going to be limited by the seeing. That means then the seeing limited scope has a resolution which is given by the lambda over R0. So any scope having a diameter, a ratio between diameter and R0 greater than 1 is seeing limited. And in that case, the IpJfhBwrmwM, for instance, for long exposure, is lambda over R0 in terms of radian. Now, if the scope has a diameter such that d over R0 is smaller than 1, you are mainly diffraction limited. And the seeing is pretty much given by the diffraction limit, which is lambda over d. And you can see on the Kolmogorov model the relationship between the IpJfhBwrmwM in arcsecond and the R0 in meter. So for our seeing, let's say 2 arcsecond, then typically we are around 5 centimeters of R0, which means the average seeing cells across the whole atmosphere seen by your scope is like 50 millimeters in size, which is typically much smaller than most of our scopes. So typically D over R0 is bigger than 1, and we are seeing limited most of the time. This table shows you a bit what this R0 is depending of the actual seeing. For 1 arcsecond is roughly 100 millimeter, a tenth of a meter. But when you go to the seeing, we usually have around 2 to 2.5 arcsecond, then it's between 56 and 44 millimeter. And then, of course, it is even less when the seeing is bad. So in this presentation, I'm going to stick around 50 millimeter, 5 centimeter for the R0, which is an average value. Now, as I said, the seeing is a statistical, it's a statistical concept because the process is stochastic, and R0 is not going to stay the same all the time. In this example here, you can see the histogram of the R0 and the variation over the season. This is for the Lick Observatory in California. And you see the median value on the histogram is around 10 centimeters, but that's typical of seeing. He has a heavy tail, meaning you have sometimes pretty good seeing, but not very often. And of course, you have good months, like in spring, and bad months in terms of seeing. And it evolves all the time, even during the imaging process, most likely over the night. There is another important parameter in seeing, is the coherence time. The tau 0, it's the time, the scale of time for which the wavefront turbulence change enough, and the change is typically back to this 1 radian or a wave over 6. And this time is based on the idea that the turbulence is moving across the field of your scope. And this motion is coming from the wind, typically, of the atmosphere. And during the motion, the structure of the seeing is not changing. If you wish, the turbulence change slower than the motion coming from the wind. And based on this assumption, which is known as the Tyler hypothesis, then the tau zero, the coherence time, is given by the ratio of the R0, which is average cell size, by the average speed of the wind. And the average speed of the wind across the atmosphere is around 10 meters per second, or 20 mph. And tau zero is also a function of wavelengths, because R0 is, but V is not, of course, and it goes, it's increasing roughly as the wavelengths. Statistic of tau, that's an histogram from the Xinglong Observatory in China. You can see the same trend. You have this histogram with an heavy tail toward the larger value, and you can see in average we are around 2 milliseconds, with a median around 1.8, roughly the same thing. So here I have a table to show you what does it mean in terms of time versus seeing. If you look at our average seeing, where you are 5 centimeters for R0, then the coherence time is 1.5 milliseconds. That's pretty fast. Now, looking at this in terms of imaging, if you take short-term image, very short, smaller than the coherence time, so which is less than a millisecond, what you do is you basically freeze, the seeing. The seeing is frozen. And when you freeze the seeing, you see these type of things. And the quality of the image, and this would be a star in this example, is all about the ratio between D and R0. When the scope is close to diffraction limit, you get something which is close to the airy disk. Not exactly, but close. When D over R0 goes up, larger aperture, or worse seeing, then you get this type of shape with some level of speckle. And of course, if you keep going, the situation becomes worse and worse. The D over R0 of 10 gives you quite a very distorted image of the star. And this goes all the way. So the number of speckles you may see on the image is roughly proportional to the ratio D over R0 square. And if you use adaptive optics, you will need roughly D over R0 degree of freedom of correction for the adaptive optic, which means you need to correct the tilt tip and higher orders depending of this D over R0. Fortunately for us, D over R0 is such that typically tilt tip will do most of the job. D over R0 decreases with roughly the wavelengths, which means it's easier to get diffraction limited operation at longer wavelengths. Of course, you lose some resolution because the diffraction limit goes up when the wavelength goes up. Let's see what's happened in terms of aberration. The atmospheric energy transfer from the atmosphere, as I said before, follow this cascade structure. It goes from the largest to the smallest scale. And the strongest energy, the largest amount of energy, is for the largest scale. The result is, when you look at the aberration, the lowest order Zernike modes get most of the effect of the seeing, which means the tilt tip. I forget the piston, which has nothing to do with the type of image we do. So if you remember for the presentation I made on the wavefront analyzing, we can always describe a wavefront as a collection of aberrations. And those are simple aberration and complex aberration. Aberration can be as simple as tilt tip of the wavefront and then defocus and astigmatism, like you can see here. The red is a peak and the blue is a trough on the wavefront. And then you have coma and so on and so forth. There is a guy named Knoll in 1976 who looked at that and describe how statistically the seeing impact those different levels of aberrations. So if you look at the total variance of the phase error, it's a function of this D over R0 ratio. So when D over R0 goes up, the error goes up, which shouldn't be surprising because we are further and further away from the diffraction limit. And then is the sum of those delta J, and those coefficients are the different type of aberration. And if you look at that, typically if you remove the tilt tip from the wavefront error, which is what most adaptive optic device will do at the very least, then the residual RMS error on the wavefront is 36%, which tells us then the tilt tip is between 60 to 70% of the deformation of the wavefront in terms of RMS error. And then when you remove the defocus and astigmatism and other order, then you get something better and better, but not that fast. So it's important to remember then, for a seeing point of view, the main effect, as you saw very early on my presentation on the first slide, is the tilt tip of the wavefront. It takes, 70% of the RMS error on the wavefront. So now let's go back to the long-term seeing, because this is pretty much what we do. So when the exposure time is way bigger than the coherence time, which is just a few milliseconds, what's happened? Then you start to average the seeing. And the seeing, when it's averaged, gives you this type of image you know pretty well, right? So the size of the star will be defined by the ratio between the wavelengths and R0. So when R0 goes up, the seeing is better, this goes down. If R0 goes down, then this goes up. Now, if you remove the tilt tip in long exposure, let's say you have an adaptive optic, then you get the same lambda over R0 ratio, but it's pretty much only a third of it. So 2/3 of the seeing is removed by taking away the tilt tip. But there is a price to pay to that, and I come back to that later. It's not that easy to truly remove the tilt tip, at least not if you have a large field of view. Here I have a profile of the typical star. This is a 11-inch scope with a 50 millimeter R0, a 5 centimeter, roughly 2 arcsecond seeing. So D over R0 is roughly around 6. In green, you see the diffraction limit of the scope, which is, a half arcsecond roughly. Now, in blue here, this is the PSF, the point spread function, the profile of the star at 550 nanometer due to that seeing. And the second blue curve is what you will get if you remove the tilt tip component. It's better, still you are not seeing limited. By the way, we clearly see then the seeing has a pretty heavy tail. So the seeing disk is pretty much, is extending pretty far away from the center. If you try to do a Gaussian fit, you see the Gaussian doesn't fit very well. They are better function than Gaussian to fit a star profile like a Moffat type of function, but that's another story. A very important concept is isoplanatic patch. And this is an angle. This is the angle for which the wavefront error remains almost the same. Back to the same definition of 1 radian, the 6th of a wave. And this angle is defined as R0 over some h, and h is an average altitude. And this is an angle for which the light going through the atmosphere for 2 different objects will pretty much cross the same path. Let's say you have a guide star over here and you have a target there. If the target is too far away from the guide star, you are not going to cross the same turbulence structure. Therefore, what's going on with the guide star, let's say you do adaptive optics or guiding, is not going to be correlated whatsoever with what's going with the target star, because the overlap may be quite small. So this angle tells you about how much this distance can be before you start not to have any correlation anymore. And it's typically few arcseconds, not much, at least in a visible band. And so that's a very nice example where you can see 60 arcsecond scale. And this is your guide star, let's say. Now, if you move away from your guide star and you look at another star, assuming you do adaptive optics, right? You try to correct the seeing, and you see what's happened. Then when you go away, the other star, let's say the target, become less and less well corrected by the adaptive optic, to the level then it becomes even worse. Because now you are so far away from the guide star, then the correction not only doesn't apply, but is even worse. You start to do wrong correction, and I'm going back to that point. So the isoplanetic patch is pretty small, and this is a very nice example of the limitation of adaptive optics. This example comes from the Palomar EO system, and they work in IR bands, 1200 to 2200 nanometer. Most adaptive optic work in infrared range because it's easier. As you saw before, everything is simpler when the wavelength goes up. R0 goes up with lambda, as well as d over R0 and everything like that. So going in infrared makes things much easier in terms of complexity and speed and degree of freedom, actuators, and all of that for the adaptive optics. But what's interesting in this picture is, first, on the left side, the Lagon Nebula, it's a zoom, open loop, no adaptive optic. You can see those two stars here cannot be resolved. When you turn the adaptive optic on, you can resolve them. And the difference is pretty big. Here, the IpJfhBwrmwM is 1.2 arcsecond. There is 0.2 arcsecond. However, when you move away from the guide star, which is one of those two stars, and you look at A and B and C stars, this is the image you can see. It's worse and worse. And this is because applying correction from this location on the field of view doesn't make any sense for C. And in between, it becomes worse and worse. Here I have a table to show you the error depending on the guide star offset. If you are offset by 0, then you get the 0.2 arcsecond. If you are offset by 5 arcsecond, it's already 0.3. At 13 arcsecond, it's not even a round star anymore. It's between 0.4 to 0.6. At 23 arcsecond, well, it's even worse. And keep in mind, this is in the IR. Invisible, it will be worse than that. Now, let's talk about what's happened when you have more or longer exposure. So the fluctuation over time, the temporal phase fluctuation, come from the spatial fluctuation. As I said earlier, we assume the turbulence is frozen, which means during the time it takes for the turbulence to cross the aperture of your scope, the turbulence doesn't change much. The turbulence cells cross the scope of some aperture faster than they can evolve. That's a fundamental hypothesis made by Tyler, and it's pretty close to the reality because of the speed of the wind. So if you use this hypothesis, you will find then when the exposure time, let's say for a guide star, is above some cutoff time, TD, then when you increase the time, you improve the seeing, the wonder of the star, for instance, as the square root of the ratio between the exposure time and TD. And TD is a function of the diameter of the scope and the ratio between T0 and T0 and R0. And this ratio is pretty much the speed of the wind. And here I have a plot that shows you that. Here you have all the effect of the seeing, and when you expose longer, then the seeing effect decreases to the level there is no more seeing anymore. That means longer exposure means you don't have any type of wonder on the star. But the star is bigger on the image, of course. So let's talk about what does it mean in terms of tilt tip and centroid if you do guiding. Centroid is a proxy for the tilt-tip of the wavefront. I say it's a proxy because in reality, the quality of the calculation of the centroid is a matter of the shape of the PSF. And if the shape of the PSF is not nice, maybe the centroid is not very good, and we'll see that later. But let's say you have a good centroid and you look at the standard deviation, how much the centroid wander, which is all about the tilt-tip of the wavefront. The wander of the centroid is a matter of the exposure time you use for guiding. And forget the equation here, it's not very important, but what's important is to understand the result. And that's an example. If you take an 11-inch scope and an average seeing of, let's say, 2.3 arcsecond, which means 5 centimeter R0, then TD is around 30 milliseconds. And the occurrence time is roughly 1.5. Exposure smaller than this TD gives you a standard deviation of the tilt-tip centroid of the guide star around half arcsecond. Now, if you increase your exposure time because you integrate longer, then your standard deviation goes down to roughly 0.1 arcsecond. And if you keep going, it's better and better. And that then shouldn't be a surprise, because when you integrate longer and longer, you average out the seeing. So this brings us to an interesting example and technique is lucky imaging. Lucky imaging is a way to deal with seeing. Time to time, a short exposure can be close to the diffraction limit. You may be lucky. Now, this is only true inside the isoplanatic patch I was talking about before. So it's not across the field of view, at least if you have a large field of view for that matter. The probability for this to happen was computed first by a Fred in 1977. So the probability for the image to be around 6 of the wavelengths is given by this equation. It's an approximation valid when d over r0 is greater than 3.5. And of course, the exposure time is smaller than the coherence time. We can compute that for any value, but the equation is more complex for a smaller d over r0. So if you see what does it mean, here I have a plot showing you the probability of success of lucky imaging, function of d over r0. So when d over r0 is small, then you are close to 100% of success rate. And then it drops pretty fast, because if you look at the equation, it's a function of the ratio d over r0 square. And this is an exponential. So it's very, very sensitive to this ratio. Now, if you go in infrared, the situation is much better. At 850 nanometer with the same seeing, then now at, let's say, d over r0 of 6, you are still pretty much 100% of rate of success, while you were around few percent in a visible band. And this is another example. If you have the same scope, an 11-inch with a 5 centimeter seeing at 550 nanometer, the probability of success of lucky imaging is roughly 0.04%, not much. Basically 1 frame every 25 frames. If you go in infrared, let's say 850 nanometer, or the seeing becomes better, which this is the same thing, then the probability goes up pretty dramatically to 70%, and now you have a success rate of 80 frames for 25. And here I have an example where you can actually see a set of 10 short exposure frames. Those are when d over r0 is 5. And you can typically see here the structure of the speckle, right, coming from the seeing effect. And sometimes it's not that bad, but most of the time it's not very good. And if you want to compute any centroid on that, good luck. So the probability to get the level of error, which is 1 radian, 6 of the wave, is only 10%. And I will argue it's probably true here. This one is probably good, and that one may be close. Now, if you decrease d over r0 because the seeing is better, you go longer wavelengths, you get that. Now, the probability of having a good image is 80%. And that's probably true as well here. Most of them are good enough to meet this 6 of the wave condition. Now, this is all about the standard model, the Kolmogorov model. This model is very useful, but it has some limitation in reality. It provides sample solutions and sample equations. And at the time, it was very interesting because we didn't have the capability of computing very complex numerical solutions. But the Kolmogorov model makes at least one fundamental assumption: is the outer scale of the turbulence, the L0, large L0, is infinite, and the small is 0. The assumption about the small is quite okay, but the large one is not true. I mean, there is no reason to believe the turbulence, the large scale, are infinite in size in the atmosphere. In fact, they are not close to that, and the difference has a significant impact on the result. So when the L0 is finite, the seeing may be quite different from what the model of Kolmogorov predicts and the reality, even for small aperture. When the lower turbulence dominates, so when the seeing is good, which is when the seeing is mainly coming from the near ground turbulence and there is a very little wind, then the L0 can be pretty small, 10 meters, sometimes down to few meters. So it's very far for infinity, and the model is very wrong. So the Kolmogorov model is worse and worse when the seeing is better and better. And the effect is mainly on the tilt tip of the wavefront, because it's all about the larger scale AD, and those have most of the energy, impact most of the low term of the aberration. And the dependency of the FWHM with the wavelengths increases in that case versus the standard Kolmogorov model. So there is another model out there. There is many models, right? I mean, there is always a way to modelize the atmosphere better than the day before. But one common model to overcome the limitation of the Kolmogorov is the von Karman model, VK model. This model explicitly accounts for the finite size of the outer scale turbulence, the L0. And this guy worked on that in 1948. You see, it's not truly new, way before computers. Worldwide, extensive measurements have been made those probably a couple of decades to look at that, and the results correlate very well with the VK model. And this is an example from the European Southern Observatory. It's a paper, I think I put the reference over here, from 2010. And here you see the FWHM in arc-second. We are in Chile, so they have a pretty good seeing, as you can see, below 1 arc-second. This is the seeing expected from the Kolmogorov model. And they know this seeing based to seeing monitors. So they monitor the seeing with special devices, and they infer the FWHM from the R0, basically coming from those monitors. Here you see what the VK model predicts, which is quite smaller when the L0 is 22 meters. And the red plot here is simulation, numerical simulation, with different diameter of telescope. In the paper, you can see actual data supporting the result. But here they do a simulation across scope size from tenths of a meter to 100 meters. And you see it's pretty much like the models will predict, except when the size of the scope has a small diameter. It has nothing to do with the scope itself. It has to do with the accuracy of the simulation. when the simulation start to work on a small diameter, the mesh used for the calculation, how many points you sample the pupil of the scope, goes down, and the accuracy of the calculation is worse and worse. There is no reason to believe you shouldn't be following this model prediction for small diameter. Actually, tests done with scope of, let's say, a 14-inch support the fact you have quite significant difference between the Kolmogorov model and the VK model. And you see when the outer scale turbulence goes down even more, like 10 meters, the difference is more drastic. So which means this VK model is a better way to modelize the atmosphere. So we can see what's happened in terms of FWHM. The VK model depends on the new parameter, which is L0 over R0. So now there is a new parameter, which is a ratio between the outer scale, who could be few meters sometime, not infinite, and the R0. And here I have a plot showing the effect of the improvement on the FWHM with a VK model versus the standard Kolmogorov model. And that's a function of the ratio between L0 and R0. In blue, you see this improvement. So when R in visible orange, 550 nanometer, when L0 over R0 is large, we are back to the Kolmogorov model. And there is no improvement because the size of the AD, large ADs are very large, and the Kolmogorov model is pretty close to the reality. But when this ratio is around 1,000, or even a bit before that, then there is a significant departure. And when you are in a few hundreds, and which is the type of situation we have when we have good seeing, then the error is between 20 up to 25, maybe 30%. And if you go in infrared, it's even more. I mean, it could be up to 35% improvement versus what the model predicts. And here I have a profile of the star with those different models. Back to the diffraction limit in blue, you see the diffraction limit at 550 nanometer and also at 850 nanometer in infrared. Now, with the Kolmogorov model in blue, you see what's supposed to happen at 550 nanometer for 11-inch and 5 centimeter seeing. In red, this is what the Kolmogorov model predicts for 850 nanometer. There is some improvement going in infrared, but not that much. It's pretty weak. However, when you use the VK model, which is much closer to the reality, the improvement in green is much obvious at 10 meter outer scale, which is the situation you will get under good seeing when most of the seeing is coming from the low, near ground turbulence. Then you will expect a significant improvement in the FWHM with this model and this small turbulence size. Now, if you look at image you take in, let's say, in red wavelengths and blue wavelengths, say you take a filter at 350 nanometer and you take let's say a narrow band, and you take a narrow band filter at 600, 700 nanometer and you compare under a good seeing the situation, then you may see a difference between 30 to 40% in FWHM, at least from the seeing point of view, if the seeing is already good. Now, you may have other problems who mask this, like tracking error and other things, but that's a trend you should see coming from the difference of wavelengths when the seeing is good. When the seeing is worse, then you see less and less difference. I mean, if the seeing is very bad, there is no things to see anymore anyway. Now, I'd like to discuss a bit what does it mean in terms of guide star and guiding. The fact you have a finite OST value improves the guide star PSF because the tilt tip is reduced and the shape of the star is better. and this improves with longer wavelengths as well. Another way to say that a better shape on a PSF, because the R0 is larger, means also a higher level of lucky imaging rate of success. As you remember, it's all about D over R0. Your scope D that didn't change, but R0 went up, and the probability of success is bigger. And if the probability of success is bigger, it's just to say then the shape of the star is less distorted by the seeing. You may still have tilt tip, the star may still wander, but the shape is better, and because the shape is better, you have a better calculation of the centroid. And that's an experiment I made a couple of months ago. I took an all-axis guider and I imaged a star with exposure time of 10 milliseconds in a visible band between 350 to roughly 750 nanometer, and in the same time in infrared above 750, roughly to 1000. And here you can see the scattered plot, and every point is the same star error. I'm not guiding here. So what I do is I'm just looking at the variation of the centroid of a star without guiding, and see how much the star wander in two wavelengths, basically two wavelength bands. And you can see here the scale are the same. There is more variation in the visible band than there is in IR. Now, the two cameras were not synchronized to the level of the coherence time. They were taking image in the same time, but not fully synchronized. However, the seeing was the same because the difference of time between those cameras was small, but not synchronized. If they were synchronized, you would expect to see the same type of spread, but with a correlation across the plot. Now, if you do the histogram, this is what you get. This is the histogram of the visible and infrared star wander. And the seeing was okay that day, and you can see the visible standard deviation is 0.5. If you remember, this is pretty much a value in a visible, which was forecasted by the model before. And here you can see in infrared you are around 0.3. So there is 30 to 40% improvement in star wander. And that's important if you use that for guiding. Now, I don't think anybody will ever guide with 10 millisecond frames, right? So the reality is you have less and less effect when you increase the exposure time. Since I'm talking about guiding, let's talk about what auto-guiding means in terms of seeing. First, the goal of auto-guiding is to correct for the setup tracking error. Those errors are independent, they are not correlated with the seeing. So, which means the tracking error from your setup is fully correlated across the field of view. Unlike seeing, there is no this isoplanatic patch anymore. If your star is moving away for any reason coming from your mechanics, well, is everywhere in the field of view. Now, you have typically two types of errors when you guide. You have long-term errors, periodic error. You can solve that with PEC. King rates error, which is the diffraction of the atmosphere, the refraction, sorry, of the atmosphere, which means the sidereal rate is not unique. It's a matter of where you are, and you can correct that, at least part of it, with a model. You have the flexure. You have the error of any model you may have, and the polar alignment error. All of that require a small correction rate. For those problems, you have a small drift, and you don't need to correct much faster than 10 seconds to minutes, depending on the quality of your mount. However, for some mounts, you may have short-term error. And those are mainly mount mechanics, gearbox type of error, or wind burst or vibration around the scope. Those may require a faster correction in a range of a few seconds. And those short-term corrections may be prone of seeing effect. So now I'm going to look at what does it mean if you have to go fast for guiding because you want to correct for the mount short-term error. The long term doesn't matter, right? Because if you can wait 10 seconds or a minute, then the thing is gone, is not part of the equation. You are far above the coherence time, which means everything is averaged out and the star doesn't wander from a seeing point of view. So let's assume for the time being, then we're going to look at correcting the tracking of the setup, and going to have some seeing involved in the process. But the first things we need to keep in mind is the goal of the tracking error we are shooting for is all about what is the seeing. If the seeing is bad, you want, put this way, if the seeing is good, you want to have good tracking. If the seeing is bad, you don't care any much, right? So this table shows you that when you have a good seeing, then you need a good tracking. The rule of thumb is you want to keep the RMS tracking error below 1/4 of the seeing, IpJfhBwrmwM. So if the seeing is excellent, then the tracking must be very good. If the seeing is good, the tracking needs to be good. If the seeing is average, the tracking may be average. And if seeing is bad, then good news, you don't need a good seeing. Sorry, a good tracking, because you already have a bad seeing. So the total RMS guiding error before you do any correction is basically the sum for a given exposure time, TC, of two components. One is the variance, or the standard deviation squared, of the tracking error from your setup. And this one usually is not a function of the exposure time. The other one is the seeing component, which is a function of the exposure time. If you remember, before we said that when you increase the exposure time, the variance of the wavefront error and the tilt tip goes down, like the square root of the exposure. So the total error you have to cope with is the sum of those two errors. Now, if you do auto-guiding with a fast enough rate, or adaptive optic, let's say you go fast enough such you cancel indeed the tracking error of your setup, you are left over with a seeing. And if you look at that, there are two situations. First, if you are inside the isoplanatic patch or outside, the total error after correction, if you start to correct for the error, assuming you corrected already the mount because you go fast enough, inside the isoplanatic patch, the error left over can be written that way. The total error is the seeing error times this 1 minus k, and this k is just a constant stretching from 0 to 1. When k is 0, you are seeing limited because you see the seeing. And when k is 0 is because you have, let's say, a long exposure for guiding and you don't correct the seeing. So you already correct the mount, unless you go too slow and the mounts start to be a problem. When k is close to 1, you are almost diffraction limited if your exposure time is below, let's say, the coherence time. So when k is close to 1, you cancel out the seeing. And that's what you could do with an adaptive optic. You can go fast enough to correct the tracking of the mount and the seeing inside the isoplanatic patch. Now, when you are outside this patch, the situation is quite different. If you have a guide star, let's say, and you have a target which is away from the guide star, let's like 50 arc seconds or 1 arc minute, the result is the error after correction is the seeing, as before, times this 1 plus k square term. And there is a square root, but so again, k is from 0 to 1. When k is 0, you are seeing limited again, like you were here. And that will happen if you wait long enough. You don't chase the seeing if you do that, right? So the result is you just get the seeing, like you get the seeing here, and you are seeing limited everywhere in your field of view. And because you were still correcting fast enough to compensate for the mount, then everything is fine. Now, if you start to push a bit the system and challenge it and go faster and faster, faster than you need to correct for the mount, but fast enough versus the seeing, then you see the situation actually goes worse. Not only you don't remove the seeing like you did before, but you make the problem worse. And this is back to this nice example where if you try to correct a target far away from the guide star, then you make the actual correction worse. Because there is no correlation between the seeing component of the guide star and the actual target. You don't cross the same atmosphere. The turbulence structure is different. Now K, this K value decreases when the exposure time goes up above the typical cutoff time I was talking about before, let's say 30 milliseconds, or at longer wavelengths. Now, keep in mind, seeing is a stochastic process. So you always want to take an exposure time long enough to be sure extreme variation are not going to be a problem, and variation of the seeing during the exposure itself, if you expose 20 minutes, is not going to be a problem either, because R0, the seeing, is not a constant, as you saw. And let me show you an example of a picture we took with my friend Mario Motta, a couple of pictures, a couple of years ago. Mario Motta is a very interesting guy. He's near Boston, and he built that scope. It's an amateur scope. I think at the time it was the biggest scope ever made by an amateur. It's roughly a meter type of scope, open at f6. And fundamentally speaking, it's true. He built the scope and then built a house around the scope. And I spent a couple of nights with him, and one of the things we did is we look at imaging with his system with different configuration. And he has, I don't know if he still do, but he has an STL 11000 SB camera with an AOL, and he was running that at few hertz to take over some of the error from the mount, because it's a big mount and it's a custom mount, and he had to do that. So this is an image of the M83 using the self-guided capability of the STL 11000. It's like an off-axis guider, basically. So we were guiding on one of those stars and closing the loop at few hertz. But the seeing wasn't very great. And the result is we were spreading the noise from the guide star everywhere on the field of view. Now, we couldn't do anything else because we had to cope with short exposure for guiding because the nature of the mount capability, the limitation of the mount. No, we just went from the visible spectrum to the infrared using, in that case, a non-axis guider. And this is what we get. We didn't change anything else. We still use the adaptive optic, the AOL. But now, because the seeing is less, then the effect of chasing the seeing on the guide star everywhere on the field of view is also less. And you have a better image, still limited by the seeing, of course. But at least from an auto-guiding point of view, you don't chase the seeing. I think if I would have to say something to summarize all of that, I would say it's always better to image when the seeing is better. If you have to image when the seeing is not as good as it could be, then you need to watch exposure time and maybe choose the right wavelengths for imaging and guiding, for that matter. And one thing you could do is to get an idea of what you're seeing is with seeing monitors, and that can be helpful to decide when to image and what type of target to image and what parameters are the best. Professional setup all do that all the time. They all the time monitor the seeing to see what they can do that night and what the possibilities are. And I think that's pretty much the end of the presentation, assuming there's still somebody here.
Yes, Gaston, thank you. There are actually a bunch of people in the room, and before I even ask my questions in the other one that I saw, feel free to type your questions into a Q&A, and I will call them right out to Gaston.
I leave the share on the screen?
No, you're fine. You can unless we decide to go back and ask you a question based on that.
Okay.
Early on, Eric asked, what exactly is a large scope? And I'm going to elaborate on that because I think early on you were saying that large scopes, and this was around when he asked the question, start to suffer from speckle. And I'm wondering where that occurs, and maybe if Eric if that doesn't represent Eric's question well, he could re-ask it more specifically.
Well, a large scope is any scope where the diameter is bigger than this R0 seeing value, the Fried parameter. Because when you go above it, you start to have some speckle. Now, I would say, based to that definition, every scope above 55 centimeter or 2 inch is a big scope.
Okay. Okay. Yeah, because because the other thing that I was wondering about was the isoplanetic patch is only, I don't know, depending on the scene, let's say 20 arc seconds. Wouldn't that mean that using adaptive optics on any sort of, I don't know, like normal scope would just be completely useless until you're really, really high resolution?
Well, that's a very interesting question because I've done some work on that long before. I used to have a Celestron CGA mount, and I was using the A08 and the AOL from SBIG, Adaptive Optics. And there are two aspects here, I think, in terms of what they bring on the loop. One, if your mount exhibits some short-term errors, the AOA may be useful to cope with the mount itself. You know, you would argue a mount, even if it's not perfect in a mechanical point of view, may be able to follow short-term correction, like let's say a second or half a second. And from a mechanical point of view, it's probably true. The inertia can be easily corrected with most of the mount. But the problem of most of the mount, at least at the time of this type of mount, then you may have backlash or things like that. I had a lot of backlash, mainly on the deck. So the best way for me to correct was to use an adaptive optic. I could correct maybe half a second and still, avoid all those backlash issues. But that's not seeing, because those errors are all across the field of view. Now, from a seeing point of view, what I've seen is when I correct around a second or half second, that's not very fast, I get some improvement across the field of view beside the mount. And I think the explanation for that is part of the seeing you may see is coming very, very close from your scope. Most of us doesn't have scope very high above the ground. So you have thermal effects, rising air coming from a nearby driveway or a roof or something like that, who can be quite correlated across the field of view of your scope, the aperture. And those, and I think SBIG have done some work on that. I mean, at the time, there's a paper from them talking about that. Although the isoplanetic patch is very small, and that's true when you are truly seeing limited from the atmosphere, the very close near ground effect coming from the observatory, for instance, may be significant for us, especially when the seeing is good. And that may make a difference. But it's true, you need to manage your expectation about adaptive optics, because even professional, right? They don't go more than few arc seconds across, and now they have this whole artificial star laser constellation solution to try to extend the field of view. But they are fighting for a fraction of an arc second. We don't.
Right.
Gaston, I have a question. Just from your presentation, it would seem like most of us that are using off-axis guiders are probably suffering that same issue of not shooting through the same, layer of air, and so the guiding from the off-axis guider would be quite inferior. Is there any relationship between, say, the size of a telescope and the use of an off-axis guider? because they're all out of the field of view, and they're all shooting through some portion of different atmosphere as the scope itself.
Well, I think if you use an off-axis guider or self-guided camera for that matter, for sure you are not tracking with a guide star in the same field of view you are imaging. So you're going to see the problem of if you go fast, right? Keep in mind, if you go fast, if you don't go fast, it doesn't matter much. Now, I would say most of the time, the isoplanetic patch from the actual seeing from the atmosphere is so small that it doesn't matter much. From the near-ground effect I was talking about before, is probably quite correlated across the whole field of view anyway. Now, which means off-axis guider will work as well. Now, all of that is only relevant if you want to correct at rate like a fraction of a second. When you correct above that, few seconds, and I'm not, if you look at the math, which was part of the presentation, you will see most of the time, if you remember the cutoff time TD I was talking about is 30-ish milliseconds. And from there, every time you multiply this by a factor of 4, you decrease the wonder of the guide star due to the seeing by a factor 2. So if you take a couple of second exposure, maybe more, seeing is very little, unless it's very bad. So if you have hurricane force wind, yes, you have a problem. But with seeing we have typically when we image, I think if you don't go too fast, you're good. Now, the problem is sometimes you don't have a hell of a choice. You have to go fast because you have to deal with your mount. And you become mount limited, basically. Now, short answer to the question is, I think it doesn't make much difference using an off-axis guider or not, because if you are truly seeing limited, then isoplanetic patch is very small. And if you are mount limited, then probably you better buy a new mount.
Yeah, because that would apply only to adaptive optics too. The isoplanetic patch, because if you're not correcting at the rate, then it doesn't matter at that fast rate.
Yes.
So
yeah, you need to correct fast to see the effect of that.
Right.
Below a second.
Yeah. So basically, for any beginners out there that are listening to this doesn't apply to auto guiding the way we're doing it. This basically only applies to adaptive optics that if you're trying to get past seeing, which is kind of a basic premise, but then again, maybe adaptive optics would help for the other things like mount issues and more localized stuff. So you can get a benefit from it, but.
Well, you see, I think I say that a bit somewhere down the presentation. When you have a very good seeing, the quality of your guiding matter.
Mm-hmm.
Because you can see, you become guiding limited, right? Mount limited or whatever. So everything you can do to improve it is important. You just need to be aware of what does it mean. If you try to beat the seeing, well, you need to know, what you are fighting with. And you may have a situation, and that's quite common for us, where the seeing is pretty much coming from very near source of turbulence, like the driveway, or you are near the ground. Even if you go in New Mexico and your observatory and your scope is just a few feet away from the ground, when you open the roof, you may have quite a bit of turbulence out there where the seeing doesn't look like close to what I said on the presentation. Because those whole theory are nice if you are in a Chile, with professional type of scope, but we are not. So all of that should be factorized in the thinking.
Yeah, it's funny you mention that, because I remember when I was building my observatory, I posted a question about should I pour a concrete floor, and somebody said no, concrete conducts or retains heat, and it ends up pouring it out into the night. And they used a thermal camera to demonstrate it, and you could actually see the footprints on the concrete. But that localized stuff is probably a bigger factor than we anticipate.
Well, if you build if you build an observatory and the scope is, let's say, 10 to 20 feet above the ground, I think you're good.
Yeah.
Now you still have the dome effect. I mean, when you open the dome, right? We have small domes. When you open the dome, you may have some effects. You have the tube effects, if the, in the scope. I mean, all of that is part, and all of that is not very well modelized with those Kolmogorov or VK model.
Right.
They are macro effects, right? Which matters, though. If you look at, I don't have the paper here, but I saw a paper from the European Southern Observatory in Chile, in Atacama, and they have this problem because the local structure, the domes and the buildings, create some local turbulence. And that's a problem. Sometimes it's more than everything else on the equation. The good news is those are typically quite well correlated across the field of view. So you may have a hope to remove some of it with adaptive optics. Of course, they have much more expensive and much more powerful adaptive optics. They correct. The Palomar example I gave you correct at, I think, few kilohertz, right? If you buy off-the-shelf as big, typically adaptive optic, you are maybe at 20 hertz at best, maybe 50, if everything goes well. So way less than what you need to be correct the seeing. So you can only correct something else, which is probably the mount and near-eye turbulence.
Now, the difference between an adaptive optics like the SBIG and a professional, don't the professional observatories that have like the pistons behind the mirrors correct for speckle and that type of thing, or whereas the SBIG would be more tip-tilt?
Yeah, well, every adaptive optics will correct at least for the tilt tip. Because I say the tilt tip in terms of RMS error is 60–70% of the error. So it's a huge amount. Now, the way it works is, if you look at the professional device, they have two types of adaptive optic system. One is just tilt tip, because it's where most of the energy is, and they remove the tilt tip first, using a tilt tip correction system with a sample mirror or something like that. And then the higher orders, in the deformation of the PSF is taken care of with the deformation of the mirror itself. The amplitude of the correction is way less. So they typically split the problem in two pieces. One is tilt tip with a sample device, and the other one is the main mirror deformation. Of course, when you buy a big product, you only deal with the tilt tip. But yet the tilt tip is a big part of the equation. If you remember, if you take away the tilt tip, right, you already get 2/3 of the effect of the seeing on the IpJfhBwrmwM. So it's way better.
Right. Yeah. That was really interesting. I don't know if anyone in the room has any more questions. I don't see anything coming in from Q&A. Anyone inside the room here? If not, I do want to thank Gaston for coming on again. He has some great presentation. Let me see. Next week, John Hayes will be on, and we're actually having the basics of statistics for astro imaging. So when we talk about stuff like RMS and standard deviation and all that stuff, you're kind of going to know what we're talking about. But this was a really cool presentation. Thank you, Gaston.
You're welcome.
Yeah,
I'll do the same presentation a bit more in detail, probably in the NIAC, in the Northeast Astro Imaging Conference. I think it's in April.
Coming up soon. What is it? Around April 10th, or I think it's.
Yeah, I think 10, 9, 10, something. I don't remember. Early April, right?
9th and 10th. Yes. Yes, because I almost scheduled the vacation that weekend, and I fixed it really quickly.
I see you there then.
Yes, definitely. All right, well, thanks for coming on. Guys out there, next week, basics of statistics, and remember, check out our website for all the stuff to contact me or anything like that.
Just a second there.
Go ahead, Alex.
When Gaston, are you speaking at NEAC or at NEAP itself?
I will be speaking at NEAC, and I will be at NEAF, but with a
conference. Thursday or Friday, you mean?
I don't know.
I think those 8th and 9th dates are Saturday, Sunday.
Yes.
Yeah. Okay, so be careful of that, so we don't give out any bad information.
No, the conference is on a Thursday and Friday, and NEAF is on the weekend.
Yeah, it's just that we said April 8th, 9th, whatever it was. Just be careful with that, guys, so that everybody knows about NEAF. You should also, in this group, know about NEAC, which is the 2 days before that. And to get the full experience, when you fly all the way from California, in my case, you really should go to all 4 days, as well as Broadway and see your release and all that other stuff. But anyway, be careful. We didn't want to give you the wrong dates on that. Check it out.
But the conference is the 7th and 8th of April, and the trade show is the 9th and 10th, which is a weekend.
Right.
And I know I'll be there, and I'll hopefully give you guys some updates from the show, all the new gear. All right, guys, thanks for coming on. I am going to let you go right now, but check us out next week.